Hi and Assalamualaikum to all my students. So we will go to chapter 4, which is entitled Field Effect Transistor, or the short name is FET. FET is divided into two parts. So for this lecture, I will cover only for the part number 1. The course outline for this lecture are types of FET, comparisons between the BJT and the FET, the JFET, and the JFET characteristics and the parameter. Field Effect Transistor, or FET. FET is a three-terminal voltage control device which is normally used in the amplification and the switching application. There are two basic types of FET. So the first one is the JFET and the second one is the MOSFET. Both of these FET is unipolar device depending on their electron or hole conduction. For FET, an electric field is established by the charge present controlling the conduction path of the output circuit without the need for the direct contact between the controlling and also the control quantities. Types of FET. Like I said just now, there are two types of FET. The first one is the JFET, which is junction field effect transistor, and the second one is MOSFET, or metal oxide semiconductor field effect transistor. The MOSFET further divided into two modes. The first one is depletion mode and the enhancement mode. Okay, so the symbol, the component here is actually referring to the electrical component of the JFET and the MOSFET. FET family. FET divided into two, which is the JFET and MOSFET. The JFET consists of depletion mode, which is divided into two, which is the N channel and P channel. And the MOSFET is divided into two modes, depletion mode and enhancement mode. Both of these modes are further divided into N channel and P channel. Comparisons between the BJT and the FET. The similarities of both components are in the application. They are used in the amplifiers, in the switching device and impedance matching circuit. The differences between both components are the FETs are voltage control device which is controlled by the parameter VGS, whereas the BJT are the current control device which is controlled by the IB. FETs are also higher input impedance, but BJT have higher gains. FET are less sensitive to temperature variations, and because of their construction, they are most easily integrated on the IC circuit. Comparisons between the BJT and the FET in terms of electrical symbol. Okay, the figure 8 is for the current control amplifier BJT. So the BJT is controlled by the base current IB, and for figure B is stand for the FET construction, which is controlled by the voltage VGS, voltage gate to the source. The JFET has two subtypes, N channel and P channel. Figure shows the physical diagram of the N channel and P channel JFET. JFET has three terminals, which are source, or the short form is S, gate, the short form is G, and the drain, the short form is D. The N-channel JFET and P-channel JFET schematic model are given in the figure. The arrow denotes the types of the JFET. The arrow showing to the gate denotes that the JFET is N-channel, and on the other hand, the arrow from the gate denotes the P-channel JFET. This arrow also indicates the polarity of PN junction, which is formed between the channel and the gate. Interestingly, in order to memorize this, the arrow of an N-channel device indicates the point in. The JFET analogy can be compared to the water spigot. The source of water pressure is the accumulation of electrons at the negative pole of the drain to the source voltage. The drain of water is the electron deficiency or hole at the positive pole of the applied voltage, and the control of the flow of water is the gate voltage that control the width of the N channel. Therefore, the current will flow from the source to the drain. The JFET, unlike a BJT which control the current flow, the transistor use current flow through the base emitter junction to control the base current. However, in the JFET, use voltage to control the current flow. By looking to the given figure, the VGG voltage level control the current flow in the VDD and RD circuit. In JFET, the current is controlled by a field that is developed by the reverse bias gate to the source junction, which is the gate is connected to the both sides. With more VGG, which is the reverse bias voltage, the field in the white grows larger. This field or the resistance limits the amount of the current flow through the RD. With low or no VGG, the current flow is the maximum. By looking to the given figure, if more VGG, the current flow is limit or minimum. With low VGG, the current flow is maximum. The N-channel JFET construction and operation. The N-channel JFET is composed of gate, source and drain. It is made with N-type silicon channel that contains of two P-type silicon terminal that placed on either side. The gate lead is connected to the P-type terminal, while the drain and the source leads connected to either ends of the N-channel silicon. The junction between the gate and the channel is reverse bias. Therefore, no current flows in the gate terminal. The greater the reverse bias, the thicker the depletion layer. The cross-sectional area of the conductive path from drain to the source, which is the area in the blue color, depends on the amount of the reverse bias between the gate and the channel. Therefore, the resistance between the drain and the source depends on the gate-to-channel bias. The pinch-off voltage Vp is the value of the gate-to-channel bias required for depletion region to extend completely across the channel. For N-channel device, current flow into the drain through the channel and out of the source, because the resistance of the channel depends on the gate to source voltage or VGS, and the drain is controlled by the voltage. There are three basic operation conditions of the JFET. The first condition is when VGS equal to 0 volt. VDS increase with some value. The second condition when VGS less than 0 volt. The VDS at some positive value. And the third condition when voltage control the resistor. We look at the first condition when VGS equal to 0 volt, therefore the VDS will increase. From figure A, the voltage VGS applied to the gate will control the current flowing between the drain and the source terminal. The figure B shows the IV characteristic curve for the graph drain current ID versus the voltage drain to the source VDS. VGS refer to the voltage applied between the gate to the source. VDS refer to the voltage applied between drain to the source. ID will increase proportionally with increasing of VDD, and the VDS increase as VDD is increased. This is called the omit region from point A to point B. The omit region is happen when VGS equal to 0, therefore the depletion layer of the channel is small and the JFET like a voltage control the resistor. For VGS equal to 0 volt, the value of VDS at which ID becomes essentially constant, which is at point B in the figure B, is called the pinch-off voltage or VP. For a given JFET, VP has a fixed value. As you can see, a continued increase in the VDS above the pinch-off voltage will produce an almost constant drain current. This value of drain current is IDSS, which stands for drain to source current with gate shorted, and it is always specified on JFET datasheet. IDSS is the maximum drain current that a specific JFET can produce, and it is always specified for the condition VGS equal to 0. Figure A shows the JFET bias at VGS equal to negative 1 volt. As VGS is set to increasingly more negative by adjusting the VGG, a family of drain characteristic curve is produced as shown in the figure B. Notice that when ID decreases as the magnitude of VGS is increased to larger negative, which causing the pinch-off lowered as well. The characteristic curve indicates the behavior of the device by increasing or decreasing current and voltage applied across the terminals. There are two types of static characteristic curve of the JFET. The first one is the output or drain characteristic curve, and the second one is the transfer characteristic curve. The output or drain characteristic curve is drawn between the drain current and the drain source voltage along the y-axis and x-axis, with gate to the source voltage as the parameter is called the drain or output characteristic. The second one, the transfer characteristic curve, by keeping the drain to the source voltage constant VDS and finding the drain current ID for various value of gate source voltage, the transfer characteristic curve can be determined experimentally. The transfer characteristic curve illustrates the voltage VGS has on ID from cut-off VGS off to pinch-off VP. Note that the transfer characteristic curve in the parabolic shape. The formula below can be used to determine the drain current. We know that for BJT, the output current IC and the input current IB are related by beta, which can be referred to the below equation. IC equal to beta IB, where the value of beta is constant and the base current IB will become the control variable. For the JFET, the relationship between the ID and VGS is defined by Shockley equation. The ID equal to IDSS multiplied with the 1 minus VGS divided by VGS off squared. So the value of IDSS will be constant, and also for the VGS off. The control variable will be the voltage gate to the source VGS. Here is the summary of the formula that is used for the JFET and BJT. For the JFET, the ID can be determined by using the Shockley equation, which is ID equal to IDSS multiplied by 1 minus VGS divided by VP squared. Because the JFET is a voltage control device, so no current flow into the gate. That is why the IG equal to 0. So therefore, the ID equal to the IS. The BJT is current control device, so we should rely on the equation that IC equal to beta IB. The value of beta is always constant, therefore the IC approximately equal to the IE. Please take note that the VBE for the silicon is always equal to 0.7 volt.